know neural networks, please give me extra comments or whatever I'm saying wrong. And like your feedback. Again, like I'm going to present from my perspective how kind of I understand them. And again, like this is more like a discussion than a lecture, I guess. So I would love to discuss and just move slowly. And feel free to interrupt me if you have any questions. Yeah, so the first is like set up how I think about like what is the goal and purpose of neural networks. Let's say we have like two collection of points in Rn1 and Rn(h). So basically you have two Euclidean space, you have collection of 2 points. Do you see the slides right now?
Yep.
Okay.
Brilliant. Thank you.
They're moving?
They are moving. Wow.
Okay, perfect. Okay, yeah. Yeah, so then the goal is we have this like two collection of points. And the first setup, I want to find some continuousless function which maps one set of the points to the other one. So, but the model space, what I'm going to define, by the model space, I'm going to define actually like the space, let's say some continuous function, or the space of probability distributions, or the space of smooth, compactly supported, or whatever, like something that I have the point cloud data or like some real data from the real world, and I'm trying to model this thing in a way that if I'm going to add some extra points or extra information, then yeah, I'm going to have like a nice approximation. So for example, like for a solution for ODEs, so I don't know. So basically this is my understanding, but in this case, I will just start with simple one. We have inputs and outputs, and I want to find or like model some continuous function that maps from X to Y. And the question is like how we can find such f. Yeah, so any questions about this one is good? Okay. Yeah, and then definition of the neural network. So how I think about definition of the neural network, that basic. Oh yeah, okay. Remind me, please. Yeah, how I think about definition of the neural network, that I want to take some representative from the same like model space. And the way how I'm going to write like this p theta is going to be composition of affine linear transformations. So that means I'm going to take my input vector of dimension n1. I'm going to apply some linear transformation and do some shift. And after this, I'm going to apply this nonlinear function sigma. And I'm going to repeat this h number of times. So each of the kind of hidden vector space in the middle, and the initial one is called like layers. And the last one is going to be output layer, and I don't apply any activation function after that. So the idea is, again, like you get your vector, you apply some linear transformation, do some shift, apply nonlinear function, and repeat this thing again, and do it like over and over. Again, like and this like p of theta and f are going to live in the same model space. So they're going to be like both continuous functions. In our original definition here, we have linear transformation AI and our like basis vectors like BI. And what I can do, I can collect them like together, and you can think like I'm going to identify them as a column vector, and I'm going to define alts, and I will call them parameters, like parameters AI and BI. In literature, people usually say AI being weights and BI being biases, but I just call them all weights because they're all important, kind of. And this is going to be a parameter space. So parameter space is going to be the dimension, how many weights do we have. And since we have multiple layers, then I will indicate by this vector like solid. And the architecture of my neural network, which I'm going to call, is how many layers do I have and what their dimension, and what activation function I'm using. Yeah.
So this AI is like a stack vector, a matrix of all the coefficients of the linear transformation.
Yeah.
And BIs are?
The shift that we're doing. So it's like biases, basically. So it's like.
Oh, I see. Oh, I got it. It's affine transformations.
Yeah. So it's like you have like A, B, C, D, for example, like X, Y, and you just add C1, C2.
Got it. Thanks.
Yeah. So you just collect all the weights together, and yeah. So this is going to be the architecture of the neural network. So just. So what objects do we have? We have a training data set. We have our neural network, which is giving us a composition of affine transformations with a nonlinear, some nonlinear activation function. We have our weights, and we have our model space in which our like neural network kind of lives, and we have our parameter space. So the next thing, like how I think about neural networks, I want to define a weight map. So what is a weight map is going to be the map from all our parameters to our model space. So that's why I prefer like to drop like continuous function or whatever, because I'm just thinking about neural networks. We have parameterization of some models. And the way how it goes that you map your parameters into your neural network. Whenever we define our model space, we can have fun, define different notion of metrics or whatever. And then we can define a loss function. So what is a loss function? Again, it's the idea that our neural network needs to approximate some real data. And what we want to do, we want real data like XY. We want to measure how successfully our neural network is approximating. So what we do, we take the output for the input for our neural network. We take the original like data that we collected like Y and comparing their like differences. And the idea is like the closer the outputs are going to be of the neural network is Y, the better our neural network is going to perform. And so the idea is like right now, like our neural network and whatever we're approximating, they're like living the same like model space M. And the question is like, so what we can do, we can just randomly like initialize some like starting weights. And in that case, because it's again like it's random, our loss function might be like pretty big. So the goal is like adjust our weights we are like gradient descending them to minimize the loss function. So for example, we're using at some point, and probably like next week talk is going to be more about this kind of gradient descent, and I'm going to skip, but so far it's like black box. You're just setting that point, you can look at every direction and just get closer to your target, basically.
Can you remind me what's big P at the top?
Big P?
Yeah.
This one. This is a parameter space.
Okay.
Yeah. So it's basically what do you have in here? You have like your AIs, BIs, and what do? You just randomly initialize your AI and BI, and whenever you're going to plug in your like axis, you will get some outputs. Well, and then you compare how far your outputs from desired ones. Yeah. Okay.
What's the point of defining capital psi here?
This is like a capital psi. Basically, I'm gonna show some slides later, but the idea is that the deep polynomial neural networks that I'm interested in are given. The question is, the idea is like for the given activation function, as I understand, sometimes the image of parameter space in model space is not going to be dense. So that's why the question is like, whenever you're going to change your activation function, your architecture, what is going to be kind of the topology of the image inside M? Because our goal that we want it to be dense in the sense that whenever you pick some model, you always want to be able to approximate that model. And apparently one of the interesting talks, I think, is going to be polynomial activation functions are usually bad because they're not going to be dense in M. So that's why I want to learn more about that. Okay.
Thanks.
So as a proposition, like for the, like, yeah.
So what you're saying about dense, so for every theta, it spits out a function.
Yeah.
Which is an element of this continuous functions between Rn and Rk. Right?
Yeah.
And then you take a subspace of this status.
Yeah.
Right? The subset. And then you evaluate its image. Right?
No, you take
Because
you take entire like
yeah,
status.
entire-
Yeah. Yeah.
And you evaluate.
Yeah. Yeah.
And
So-
you evaluate the image of this psi.
Yeah. So for example, like stupid example, if you will make activation function be activation function being 0, then it's going to be just a point in your model space. Yeah. not a point. But yes, I think it's gonna be just a point. Yeah, that's it. So yeah.
It's just a technical detail, but like the activation function is included in this p theta, right?
Yeah. Yeah, so the idea is like there is so different ways how we can set up different models what we want to approximate, and for all depends what we want to do, we need to use different architectures. That's why we have like convolutional large language models and others. So yeah, what I'm interested again, like my entrance to these neural networks was from more like mathematical perspective. So I don't know a lot about the actual like let's say like building blocks of it. So for example, I'll never learn properly what is universal approximation theorem and like what is the point of it. Or when we have like overfitting. So apparently if you have just a lot of points, you can just find really like kind of nice polynomial which will fit every other point. But if you add an extra point, kind of that's going to be a problem. Yeah, so that's why you don't want like kind of to overfit. We want to be able to generalize our neural networks. Getting stuck in local minima is also like really interesting. Like when we have a landscape of the loss function and what architecture again like to use and how to build and train our neural networks so we're not going to get stuck. And best initialization of starting parameters. So depending like how we're going to initialize them, we might be successful or not successful in training our neural networks. That's also pretty interesting. Way to optimize, for example, stochastic gradient descent and an optimizer. I don't know what is that. No, I don't like I use it, but to learn more about different ways to optimize and how they affect your architectures. That's interesting. And as I said, like different models require different neural network architectures. So that's why we have like 3 proposed like papers. It's like the topology of deep neural networks and neural networks related to medicine and ODEs, I believe, or something. Yeah, so that's why I feel like if so what is going to be the plan that for the next 3 talks or 4 talks we have people covered. And if you're interested to give a talk on any of this, please let us know. And we have also like 3 papers. So the goal is probably going to give our sequence of talks, and then we can have 1 or 2, like 1 session, like for practice, just when we actually sit down and do something with neural networks. Yeah, so we can do whatever we want. So my personal goal is just more understand like kind of this topology of the neural networks. There's like 2 different ways that you can do. You can either like to see if you, for example, training on some like data set which has a lot of symmetries, how much stuff the neural networks is going to remember itself. So there's like a really nice papers about like equivariant like neural networks. Or like another thing, like when we have some intelligent element for like some, let's say like for some manifolds, and you have deep neural networks with RLU function, and you want to see how the Bethe numbers changes when you kind of to traverse like your point cloud approximation of your manifold through each layer. That's also like really interesting. So that's my personal interest, but also I want to learn more about like ODEs or like how other people do neural networks for their own sake and stuff. Yeah. Anyway, so this is what kind of my interest. It's like deep polynomial neural network. So now we're gonna be like to go like into more specific about details. So first, we don't have a bias. So what that means? It means for each layer, we're going to apply only like linear transformation. Then what is going to be our activation function? Our activation function is going to be a monomial. So that means whenever you're going to input some vector, the output is going to be, you take every coordinate and raise to the power of your monomial. And what is going to be output in our case? So output, like I'm going to show you the example, but the idea is like in each procedure, what you're going to take? You're going to take some vector, multiply some linear transformation, raise to some power. And actually what you can observe that as an output, like in every coordinate, you're going to have a homogeneous polynomial. So your model space actually be, since we have like, okay, there are like some typos, this H, you have like H coordinates that means like your model space is going to be the product of H symmetric spaces, where if you haven't seen like the space of symmetric spaces, basically I'm saying it's space of homogeneous polynomials of this degree and n1 variables. Okay, concrete example. So what I'm going to take the architecture is like 3, 2, 1, and r is equal to 2. So that means my input vector is going to have 3 dimension, my hidden layer has 2 dimension, and my output is going to be 1 dimensional. And my activation function is going to be R2. Yeah, so I'm going to stop here for a second if you have any questions.
Okay,
But-
when you consider this setting, like the polynomial neural network, do you think this can achieve like equivalent performance, I mean, comparable performance to those general network?
Yeah, so one of the reasons why, because I'm not going to talk about this today, but I'm happy like to give another one, is I can do CP approximation of symmetric tensors, and or like finding CP rank of symmetric tensors, and they're like embedded kind of in this.
I see.
Yeah. So for example, when I'm training my neural network, and when my last function is going to drop to 0, the weights are going to be actually my kind of decomposition of my symmetric tensor. And it's really interesting, like, to look at the basically this is my interest is purely like not applied. For me, I'm just thinking about this neural networks as algebraic. When you take the closure, I will show you it's going to be algebraic variety. And so I just thinking about them more like from algebraic geometry perspective. It's really interesting to study them. Yeah.
Thank you.
Yeah. Yeah, sorry, Fran, you were asking something?
So the r equals 2 means we're just squaring
Yeah.
everything.
Yeah.
So if you picked r equals 4, we were just going to cube. Like that's what like row of sub n is doing. It's just like squaring everything.
Yeah. In the next slide, I have actually written them in coordinates, so we can stare together like for a couple of minutes too. Yeah. So for example, in this case, 3, 2, 1, what that means, I'm going to give a spoiler. That means I have 3 by 3 symmetric matrices, and I will try to approximate them with rank 2 matrices, because like kind of the hidden layer in this case will control the rank of your approximation up to which you can go. Yeah. Any other questions? Yeah. So
I have another question.
yeah.
Is this class of model dense in homogeneous models? Like, is this dense in homogeneous functions?
Actually, no. That's interesting. That's the question. The question is how big you need to make your hidden layer to make it dense. And by making dense, it's exactly finding the CP rank. Because what I'm trying to say, like when R is going to be equal to 3 and we're going to approximate kind of symmetric tensor. So as soon as it's going to become dense, that means we're going to find kind of the border rank of the tensor.
Nice.
Yeah. So example, we have like W1 and W2, which are given by AIJ and VK. And so what I do, I take my like first matrix, multiply by my x1, x2, x3, and then I square it. So what I'm going to obtain, kind of this two-dimensional vector with this input like a11 x1 plus a12 x2 plus a13 x3. But how I can think about this? I can think about this as a linear functional. So I'm going to write this as just qi, yes? And so if I will just replace all this kind of my row vector times my column vector as applying my linear functional to this kind of xi, x1, x2, x3, then I can write my output as bq1 squared plus bq2 squared. But if you're going to look here on the bottom, if I'm going to replace them back, and we have kind of this algebraic expression, if you're going to multiply it out and add it, you're exactly going to have a quadratic form on 3 variables. Does it make sense? Yeah. So okay, let's see, what's on my next slide? I don't remember. Okay, yeah. So what does it mean? It means right now I have my parameter space, which is going to be 8-dimensional. And my like model space is going to be, in this case, a quadratic forms on 3 variables. So it's going to be 6-dimensional. And the image of my kind of the weight map, the friends that you were asking, I'm mapping kind of, I have like 8-dimensional. I'm mapping the kind of this 8-dimensional space into the 6th-dimension via this parameterization. And the question is like, is this thing is going to be dense? And the answer is no, because whenever you're going to have like this expression over here, that means that you're going to take your quadratic form on 3 variables, and you will try to approximate it with so one of the way to think about this, whenever you have a quadratic form, you have a 3x3 symmetric matrix. And here, what I have? I'm going to have the sum of 2 symmetric matrices of rank 1. So I'm trying kind of to approximate this 3x3 full rank matrix with rank 2 matrices, and that's kind of not possible. So that's why it's not going to be dense. Yeah. Let's see. Okay, so I'm talking more about, okay, so and here, like algebraic geometry perspective right now. So I'm going to take the image of my of like kind of this like weight map. And the image itself, when I'm going to work like over complex, is not going to be kind of the variety. But as soon as I'm going to take the Zariski closure, it's suddenly going to become like a variety. Over real numbers, it's actually going to be a semi-algebraic set. And what is the question we can ask? We can ask, okay, so I have right now the closure of this, this M should be different, the closure of the image. I use the same M for the model and for this one. Yeah, sorry about that. But basically, this M is different from the model space. Let's think about this like as big N. So I have the closure of the image in my model space, and the question is when this closure is going to be equal to the entire space. So when it's equal to the entire space, it's going to be kind of called filling. But when the image itself is not going to be the entire space, but is going to be like dense in my model space, then we're going to call it thick. So the question, like from algebraic geometry perspective, that some people are answering is like, okay, so right now, like for different architectures, give like a description or like find like the ideals for like these varieties and how they look like and blah blah blah. So that's the question. So for my kind of main interest, what I do, one of the things that I'm thinking is like single output networks. So that means I have like this architecture. So we have n inputs. The hidden layer is going to be m-dimensional. And if I'm going to write down the image of my neural network is going to be given as the sum of m linear functionals to the power of r. And so here, like if you're familiar with tensors, that means I'm trying to approximate kind of symmetric tensor or a symmetric R tensor with rank 1. And the question is like, whenever I'm going to make my M big enough, we'll be able to do it, and that will be like actually my border rank. Yeah, sorry, I'm just putting like a lot of adjectives like border rank and stuff, but I just didn't want to. I'm just trying to show like what like I'm thinking about when yeah. It's the dimension of the output. Yeah. So the idea, like overall, like to understand, like you can use this kind of single output neural networks to approximate CP rank of symmetric tensors. So that's kind of the main goal. So for example, like when R is equal to 2, let's come back to our to our like quadratic forms. In this case, the image is going to be given by kind of this sum. So the question is, when the image of my weight map is going to be equal to the entire space. So in other words, it means whenever I'm going to take some quadratic form, what dimension for my hidden layer do I need to pick to make sure that I'm going to hit this quadratic form for some weights? But if you will think in terms of like symmetric matrices, that means whenever you're given symmetric matrix of rank n, how many times do you need to add rank 1 matrices to, how many like rank 1 matrices do you need to add to kind of reconstruct the original matrix A? And since we work in a world of like matrices and they behave real nicely, we know that the rank of A, as one kind of equivalent definition, is to write A as a sum of n rank 1 matrices. So that's why we know that M must be equal to N. And the story for when it's filling, it's done. Oh, in this case also, when you take the closure, nothing changes. So it's dense, yeah. So here, like the next question, which is like interesting is, okay, but what if I'm going to take like N, and let's say M is going to be N minus 1. And then you want to find the variety of this in sim2Rn, how it looks like. But that means I want to have symmetric matrices of rank N minus 1. So that means determinant of the entire matrix must be 0. So that's why the variety, the image that is the variety is going to be cut out. The image of my neural network is going to be exactly like kind of this determinant of symmetric matrix is equal to 0. And the question is like, okay, well, now I will change my R like to different, like cube and fourth. Can I find like cutting equations of the Zariski closure of the image of the neural network or not? So coming back to our previous example that we did, I decided just to pick one example, kind of to return to it over and over again. So we start again like with 8 parameters. And the parameterization of symmetric matrix is going to look like this. See what's there. Okay, yeah. If you will take the determinant of this matrix, the determinant is going to be equal to 0. And that's exactly is going to be parameterization in terms of your AIJs and BKs of your like variety, which is that 0. And we can repeat the same thing for higher R. So basically, and here I just want to show like the example when I'm going to take R is equal to 3, and I'm going to take the homogeneous polynomial like on 3 variables. So what I'm going to do, I'm going to take, let's say, like this polynomial, yes, homogeneous polynomial. And this is actually going to be an algebraic curve for which when lambda is equal to -3, it's going to have like singularities. And the cool part that if I want to make my neural network dense in the space of homogeneous polynomials of degree 3 in 3 variables, then M just needs to be equal to when lambda is equal M is needs to just to be equal to 4 when lambda doesn't equal to -3. But as soon as I'm going to be, we'll have like singularity, then I suddenly need to increase my rank by 1. So I will need at least like, so that means if I have this symmetric tensor, I will need to add a rank 1 tensors at least like 5 times to reconstruct the original one. Yeah, so in this case, this is the first example when I have the image of kind of my neural manifold of my neural network when I'm which doesn't equal to its closure, which is going to be like the entire space. But as soon as I'm going to hit M is equal to 5, the image of my neural network is going to be the entire space. And this slide, okay, so I actually want to show some example also, and then we can have discussion. And this just one simple example that if I'm going to take different architecture, then instead of CP kind of rank decomposition, I will try to decompose my tensor, my symmetric tensor in this form. So I will try to decompose it as a kind of this sum of product of even powers of linear forms. And what is like interesting, like to see what kind of different tensor decomposition can show up from this kind of neural network perspective. Okay, so unfortunately, I have some code here which I'm going to show right now. And I don't have it here, so I will just rotate my laptop. So let me share my screen. What I'm going to do, I'm going to take the function like x squared plus y squared plus z squared, and I'm going to consider like the level surfaces of this function. And this is going to be just concentrated spheres. So in some sense, you can think that you have a room, and this kind of the heat map of the temperature of the room or something like that. And then I will try and go like kind of train my neural network. And when I'm going to train it, I will go and plot it. And so what do you have here? If you will kind of try to visualize, here I have the neural network architecture like 3 to 1. So that means I have quadratic forms, which is like of full rank. So I have like x squared plus y squared plus z squared, which is a sphere. And I'm trying to approximate these quadratic forms with rank of rank 2. So that means I'm trying to approximate something as like x squared plus y squared. And here you can see, you can imagine the cylinder. So neural network is trying to learn kind of the level surface of the spheres, but it has capability over like at most like rank 2. So it means it can approximate your spheres only like either like with 2 planes kind of, or like with cylinders. So that's why we're going to get a cylinder there. But if I will, let's say, try to run it like once more. Okay, so let's see what I'm going to get. Okay, here again, I have a cylinder. But basically the idea is like, and let me try to change the architecture to be equal, let's say like 4, the middle layer. Okay, let's see. Okay, this is also sometimes needs to train a couple of times because we got stack. Okay, so when is equal to 4, I got like sphere back. Yeah. So basically that's it. So I want like probably for 10 minutes just to discuss and ask questions. And that's the idea. So the idea is like you have this kind of the space of symmetric tensors. You can find like different tensor decomposition, and training neural network and understanding it is important because sometimes like in algebraic statistics, they have all this like, or like principal component analysis or some other stuff. They need to find a lot of the standard decomposition. So like these neural networks can help you, probably not in the most optimal way, but use these neural networks to find it. Yeah. Okay, so I'm done.